Welcome to AMR training. This lesson explains the main transmission systems used in earth-moving equipment, from old mechanical machines to modern electronic powershift, hydrostatic, continuously variable, power split, and electric drive machines. We will not only name the parts. We will follow every command. You will see what the operator moves, which interlock must be satisfied, which controller or linkage responds, which solenoid or valve moves, where pressure travels, which clutch, pump, motor, or gear becomes active, and how torque finally reaches the tires or tracks. The exact arrangement differs by manufacturer and model, so always use the correct service information for the serial number. But once you understand these common building blocks, unfamiliar machines become much easier to diagnose. An engine normally turns in one direction and works efficiently over a limited speed range. A machine, however, must start from rest, move forward or reverse, crawl with heavy load, travel faster with light load, and stop without stopping the engine. The transmission solves those problems. First, it provides neutral, which interrupts the torque path. Second, it selects direction. Third, it changes the ratio. Low gear reduces speed and increases wheel or track torque, while high gear allows more travel speed. Fourth, it cushions engagement so the driveline is not shocked. Some systems do this with a clutch, some with oil in a torque converter, some with variable pump displacement, and some with an electric motor. The final drives then provide the last speed reduction before the sprocket or wheel. Begin every diagnosis by drawing the power path. In a conventional machine, the engine drives a flywheel or torque converter. Power then enters a gearbox, passes through a transfer gear or propeller shaft, crosses a differential or steering unit, enters the final drives, and reaches the tires or tracks. A hydrostatic machine replaces much of that mechanical path with a hydraulic pump, high-pressure hoses, and one or more hydraulic motors. An electric drive machine uses a generator, power electronics, and traction motors. The path may look different, but the question remains the same. Where does energy enter, where is it controlled, and where does it stop? The colored torque line on screen will remain bright only through components that are carrying power. That is the simplest way to understand neutral gear engagement and a loss of drive. On a modern machine, moving the direction lever does not usually apply a clutch directly. The lever sends an electrical input to a transmission controller. The controller first checks conditions such as parking brake status, neutral start logic, seat or armrest switch, engine speed, oil temperature, transmission speed, and active faults. If the command is permitted, the controller sends current to a proportional solenoid. The solenoid moves a pilot valve. Pilot pressure moves a larger control spool. Main transmission oil fills a clutch piston cavity. The piston compresses alternating friction discs and steel plates. When the clutch can hold torque, the selected gear becomes active. Speed sensors then confirm that input and output speeds changed as expected. Older machines may replace the controller and solenoid with rods, cables, or a manual valve, but the hydraulic clutch action is similar. Before blaming the transmission, understand the interlocks. Many machines require the direction control to be in neutral before the engine will start. Drive may remain disabled if the parking brake is applied, the operator is not detected, a skid steer restraint bar is raised, a hydraulic lockout is active, or transmission oil pressure is unsafe. Some systems force neutral when a door opens or when the control lever and actual gear disagree. An inching or neutralizer pedal can intentionally remove or reduce clutch pressure even though the direction lever says forward. The controller may also limit gear or lockup during cold oil, excessive temperature, overspeed, or a sensor fault. Therefore, the first check for a no-move complaint is not disassembly. Confirm the display, warning lamps, brake release, interlock inputs, selector status, and diagnostic codes. Transmission oil is not merely a lubricant. A charging section of the pump supplies control pressure. That pressure fills clutch pistons and moves valves. A lubrication circuit feeds gears, bearings, bushings, and clutch plates. A cooling circuit carries heat to an oil cooler, and filters remove damaging particles. Some large machines also use scavenge pumps to return oil from low housings to a tank or main sump. The correct oil level, viscosity, and specification are essential. Low oil can draw air, causing delayed engagement and pressure fluctuation. Too much oil can foam and overheat. Wrong oil changes friction behavior and shift quality. Contaminated oil can stick a precision spool or damage a pump. Always check oil at the specified temperature, engine condition, and machine position because the correct procedure varies by model. A torque converter is a fluid coupling with three main rotating elements. The engine turns the impeller. The impeller accelerates oil outward and sends it into the turbine. The turbine turns the transmission input shaft. Oil leaving the turbine meets the stator. At large speed difference, the stator redirects the returning oil so it helps the impeller instead of opposing it. This produces torque multiplication. At near coupling speed, oil flow changes and the stator overruns on its one-way clutch. Because power crosses through moving oil, the engine can run while the machine is stopped in gear. The disadvantage is slip, which produces heat and reduces efficiency. A converter therefore needs correct inlet pressure, outlet pressure, flow, cooling, and stall speed behavior. This section is a short bridge from our previous detailed converter lesson. A lockup clutch removes converter slip when conditions are suitable. The controller watches selected gear, engine speed, output speed, throttle or load, temperatures, and brake commands. When lockup is allowed, it energizes a lockup solenoid. The solenoid changes pilot pressure in the lockup control valve. Regulated oil moves the lockup piston and clamps a friction disc or plate pack, mechanically connecting the converter cover or impeller side to the turbine and output shaft. The torque path becomes direct and heat generation falls. During a shift, heavy lug, braking event, or low speed, the controller releases or modulates the clutch so the converter can cushion torque again. If lockup never applies, the machine may feel weak or hot at travel speed. If it stays applied at the wrong time, engagement can be harsh or the engine can lug. Older and smaller machines may use a mechanical manual transmission. The engine flywheel drives a dry single-plate or multi-plate clutch. With the pedal released, springs clamp the friction plate between the flywheel and pressure plate, so torque enters the gearbox. Pressing the pedal moves a cable, rod, or hydraulic release system. The release bearing pushes the pressure plate fingers. Clamp force is removed, and the gearbox input shaft is disconnected. The operator then moves a gear lever. Selector rails and forks slide gears or synchronizer sleeves to establish the required ratio and direction. Releasing the pedal gradually restores clamp force. This system is simple and efficient, but it interrupts power during shifts and depends heavily on operator technique. Excessive slipping overheats the clutch. Incorrect free play can cause incomplete release or constant bearing load. Most Powershift transmissions use wet multi-disc clutch packs. Friction discs are splined to one rotating member. Steel plates are splined or tabbed to another member, often a drum or housing. When the clutch is released, return springs move the piston back and the plates separate enough to slip freely in cooling oil. When apply oil enters behind the piston, pressure times piston area creates clamp force. The piston compresses the stack, friction locks the two members together, and torque crosses the clutch. A clutch can connect a gear to a shaft, hold a planetary member stationary, or select forward and reverse. Engagement is not simply on or off. The control valve fills the piston cavity quickly, then raises pressure at a controlled rate. That fill and modulation prevent flare, overlap, and driveline shock. Worn seals, warped plates, or low pressure cause slip and heat. A power shuttle is common on backhoe loaders and similar machines. A torque converter allows the engine to remain running while stationary. The transmission has hydraulic forward and reverse clutch packs, while the operator may select the main speed ranges with a mechanical lever. Moving the shuttle lever to forward sends a mechanical, hydraulic, or electrical command to the control valve. The forward clutch receives oil, its piston applies the plate pack, and torque follows the forward gear train. Reverse releases the forward clutch and applies the reverse clutch, changing the direction of rotation. The clutch cutoff or dump button temporarily vents shuttle clutch pressure, so the operator can change range or raise engine speed for hydraulics. Advantages are simple direction changes and good low-speed control. Disadvantages include converter heat and clutch where if direction changes are made at excessive ground speed or high throttle. A countershaft power shift uses several parallel shafts with gears that remain in mesh. The gears can rotate freely until a hydraulic clutch locks a selected gear or clutch drum to its shaft. Direction clutches establish forward or reverse. Speed clutches choose the ratio. The operator requests a direction and gear, but the controller decides the exact engagement timing. It applies one direction clutch and one speed clutch, creating a continuous torque route through the selected pair of gears. Because the next gear is already meshed, the transmission can change ratio under power by releasing one clutch while filling another. Wheel loaders, graders, haulers, and backhoe loaders often use versions of this architecture. It provides efficient direct mechanical power and many ratios, but it needs precise clutch modulation. A leaking piston seal or a dragging clutch can disturb more than one gear because several members share the same shafts. A good power shift is a controlled transfer of torque. First comes clutch fill. The controller commands enough current to move the solenoid and quickly fill the empty piston cavity, but pressure remains low until plate clearance is taken up. Next is the torque phase. Pressure in the oncoming clutch rises while the offgoing clutch reduces its capacity. Torque transfers without a complete loss of drive. Then comes the inertia phase where the rotating members change speed to match the new ratio. Finally, the clutch reaches full holding pressure. If the oncoming clutch applies too late, engine speed flares and the machine hesitates. If it applies too early while the old clutch still holds, both ratios fight each other, causing a tie-up and harsh deceleration. Oil temperature, clutch wear, seal leakage, engine torque reduction, and calibration all affect this sequence. A proportional or pulse-width modulated solenoid is the bridge between electronics and hydraulics. The controller does not merely switch it on. It changes average current. Magnetic force moves the armature or pilot spool against a spring. That changes pilot pressure at the end of a larger regulating spool. The regulating spool meters main pump oil to the clutch while feedback oil balances the spring and solenoid forces. More commanded current may increase or decrease clutch pressure depending on the valve design, so never assume the direction without the schematic. The controller uses a calibrated current profile to control fill time and pressure rise. Electrical resistance can be correct while the valve is still mechanically stuck. Likewise, good current cannot create pressure if pump supply is low. Diagnose the electrical command, pilot stage, main pressure, and clutch circuit as separate parts of one chain. A simple planetary gear set has a sun gear in the center, planet gears mounted on a carrier, and an internal ring gear around them. All teeth remain meshed. A gear ratio is created by driving one member, holding another, and taking output from the third. For example, drive the sun, hold the ring, and the carrier turns forward more slowly with increased torque. Drive the sun, hold the carrier, and the ring turns in reverse. Lock any two members together and the entire set rotates as one unit in direct drive. If no member is held, the set can freewheel and transmit little useful torque. This is why planetary transmissions use clutches as both connectors and brakes. One clutch may connect engine input to a member, while another clutch holds a different member to the case. The selected combination creates direction and ratio. In a planetary power shift, several planetary sets share shafts and carriers. Multi-disc clutches connect rotating members together or hold a member to the transmission case. To select a gear, the controller energizes the required modulating valves. Oil moves each clutch piston. The chosen friction stacks lock their members, and a specific torque path forms through the planetary sets. A typical machine may use one clutch for direction and another for speed, while a different design may use two clutches for every range. Neutral is created by releasing the necessary torque-carrying clutch, not by moving gears out of mesh. Planetary units are compact, strong, and well-suited to high torque. They also hide the power path inside nested components, so a clutch application chart is essential. Never guess which clutch should be pressurized. Use the model-specific chart, hydraulic schematic, and pressure taps. A clutch application chart is the fastest way to connect a symptom to a circuit. Imagine a 6-clutch planetary transmission. First forward might require clutch 1 and clutch 5. Second forward may keep clutch 1 and exchange clutch 5 for clutch 4. Reverse may use clutch 2 plus a speed clutch. If first and second forward both fail but reverse works, look for the clutch or hydraulic supply shared by those forward gears. If only one ratio fails in both directions, suspect the speed clutch used only in that ratio. If every gear is weak, look upstream at oil level, pump supply, main relief pressure, converter, inching circuit, or a common electronic inhibit. The combinations on screen are examples only. Real clutch numbers differ between models. Always copy the correct chart before testing so every pressure reading has meaning. Many track-type tractors use a torque divider ahead of the Powershift transmission. It combines a torque converter with a planetary gear set. Part of the engine torque can pass mechanically through the planetary path, while the remainder passes through the converter. The two paths combine at the output. Under light load, the mechanical contribution improves efficiency. As load increases and output slows, converter multiplication increases, helping the machine push without stalling the engine. The exact member connections vary by design, but the important idea is two simultaneous paths, not a simple converter by itself. Some large dozers add an electronically controlled stator clutch. By allowing or preventing stator reaction, the system changes converter capacity and controls how much torque reaches the driveline. Diagnosis may therefore involve converter pressures, stator clutch command, outlet speed, and the downstream Powershift transmission. An automatic Powershift controller chooses gear from machine speed, engine speed, throttle demand, load, direction, brake input, slope information, and selected operating mode. During an upshift, it may request temporary engine torque reduction over the data link. That reduces stress while the offgoing clutch releases and the oncoming clutch applies. During a downshift, it checks that engine speed will not exceed the safe limit. Lockup may release for the shift and reapply afterwards. Kickdown logic selects a lower ratio when the operator needs more torque. Some loaders automatically shift to neutral or reduce rim pull when the brake pedal is pressed, preserving hydraulic power and reducing brake wear. A fault in an engine speed sensor, output speed sensor, data link, or brake input can therefore change shift behavior even when the clutches are mechanically sound. A hydrostatic transmission converts mechanical power to hydraulic power and back again. The engine drives a variable displacement axial piston pump. High-pressure oil from the pump flows through one side of a closed loop to a hydraulic motor. The motor turns the final drive. Oil returns through the other loop line to the pump. In neutral, the pump swashplate is near zero angle, so piston stroke and loop flow are near zero even though the pump shaft is rotating. To move forward, the control system tilts the swashplate in one direction. Flow increases and the motor turns forward. Tilt it through neutral in the opposite direction and flow reverses, so the motor reverses without a mechanical reverse gear. Changing pump displacement changes travel speed and available torque. Some systems also vary motor displacement to extend the speed range. The pump swashplate is usually too heavily loaded to move directly by an operator lever. On an electronic system, the travel lever or pedal sends a position signal to the powertrain controller. Interlocks and engine conditions are checked. The controller then commands one or two proportional displacement solenoids. The solenoid meters charge or control oil to a servo piston on one side of the swashplate. Servo pressure overcomes the centering mechanism and tilts the plate. Pump pistons now make a longer stroke, creating loop flow. A swashplate position sensor or calculated pump response provides feedback. When the operator returns to neutral, command current reduces, servo pressure balances, and springs center the plate. On older pilot-operated systems, a mechanical lever moves a pilot valve, but servo oil still provides the force. A bad lever signal can therefore look like a hydraulic pump problem. Compact track loaders and hydrostatic dozers often use two drive paths, one for each side. Each path may have its own pump and motor, or a shared pump arrangement with separate control. Command both sides forward at equal speed and the machine travels straight. Reduce flow to the left motor while maintaining the right side and the machine turns left. Reverse the left side while the right continues forward and the machine counter-rotates. The steering lever or joysticks send desired speed and direction to the controller. The controller calculates separate left and right pump or motor commands, then drives the corresponding displacement solenoids. Speed sensors allow correction so the tracks remain synchronized. A machine pulling to one side can therefore be caused by control calibration, unequal pump displacement, motor leakage, final drive drag, track tension, or an engine load problem, not only by a steering joystick. A closed hydrostatic loop cannot survive on loop oil alone. A charge pump draws filtered oil from the tank and maintains positive pressure in the low-pressure side. Check valves route charge oil to whichever loop line is returning from the motor. This replaces leakage, prevents cavitation, and supplies control and cooling flow. A flushing valve removes a controlled amount of hot oil from the low-pressure side and sends it through the cooler and filter. High-pressure relief or crossover relief valves protect the loop from extreme load. Make-up valves help prevent a vacuum during rapid deceleration or overrunning load. Pump and motor cases have drain lines that carry internal leakage back to tank. Excessive case drain flow is an important sign of worn rotating groups, but the correct limit and test temperature must come from service information. Never cap a case drain on a running unit. The housing can fail. Hydrostatic ratio is controlled by displacement rather than fixed gear teeth. Large pump displacement sends more flow for a given engine speed. Large motor displacement produces more torque for a given pressure but less speed. For strong low-speed push, the controller commands high motor displacement and manages pump displacement so loop pressure stays within limits. As the machine accelerates, it can reduce motor displacement and increase the effective travel ratio. Engine anti-stall logic watches engine speed and reduces pump demand before the engine stalls. A decel pedal may reduce engine speed, hydrostatic command, or both, depending on the machine. When the operator releases travel command, the system can use hydrostatic braking by reducing or reversing pump torque, but mechanical service and parking brakes are still required. Efficiency falls if the machine is held at high pressure with little movement because energy becomes heat. A continuously variable transmission changes ratio without the distinct steps of a normal power shift. In earth-moving equipment, the term often describes a hydromechanical or power split system rather than a belt-type automotive CVT. The controller can adjust hydraulic pump and motor displacement while mechanical gears carry part of the power. This allows ground speed and engine speed to be controlled more independently. The operator may request a travel speed while the controller selects an engine operating point that balances fuel. A power split driveline sends engine power along two parallel routes. One route is mechanical through gears. The other route is hydrostatic through a variable pump and motor. A planetary or summing gear combines the two at the output. At low speed, the hydrostatic branch provides precise control and high tractive effort. As speed rises, in an electric drive dozer or haul truck, the diesel engine turns a generator instead of a conventional multi-speed transmission. Generated electrical power passes through a DC link and power electronics. Inverters control current and frequency to the traction motors. The motors turn reduction gears and final drives at the wheels or tracks. The operator's travel command goes to a controller, which calculates required motor torque and sends gate commands to the inverters. At low speed, electric motors can produce strong controlled torque without a torque converter. During retarding, the motors act as generators. The electrical energy may be dissipated in resistor grids, used by other loads, or stored in a hybrid system if the machine is designed for storage. Advantages include smooth torque control and fewer mechanical gear changes. Hazards include lethal voltage and stored energy, so only trained personnel using the OEM isolation procedure may test high-voltage circuits. Will loaders use several driveline types? A conventional loader has a torque converter, countershaft or planetary power shift, transfer gears, axles, differentials, and planetary final drives. Modern units may add lockup in several gears. Some use an impeller clutch or rim pull control. Brake pedal position commands a valve that reduces pressure on an impeller clutch, lowering torque to the wheels while maintaining engine speed for the implement hydraulics. Others use transmission clutch neutralization or modulation. Advanced loaders may use a power split CVT. In every case, the operator needs controlled approach speed while filling or dumping the bucket. Do not assume an inching pedal always vents the same clutch. It may modulate a transmission clutch, an impeller clutch, hydrostatic displacement, or a software torque request. Identify the architecture before interpreting pedal pressure, slippage, or heat. Track-type tractors commonly use one of three layouts. Traditional larger dozers use a torque divider, planetary power shift transmission, bevel or differential steering system, and final drives. Hydrostatic dozers use separate controlled hydraulic paths to the left and right tracks, making steering and speed continuously variable. Electric drive dozers use a generator and traction motors with final reduction gears. On a power shift dozer, the direction and gear selector commands transmission clutches, while steering may be achieved by differential steering or controlled clutch and brake systems depending on the design. On a hydrostatic dozer, the steering input changes the relative left and right motor speeds. On an electric dozer, it changes left and right motor torque. The final symptom may feel similar, but the activation chain and test points are completely different. First, identify the machine's actual powertrain architecture. Skid steers and compact track loaders usually use dual hydrostatic drive. The engine drives one or more pumps, and separate hydraulic motors power the left and right chain cases or final drives. Steering is created by speed difference between the sides. These machines also use strong safety interlocks. The seat switch, restraint bar, parking brake, hydraulic lockout, door switch on some cabs, and controller status can prevent drive. The joysticks may be mechanical over hydraulic, pilot hydraulic, or fully electronic. On an electronic system, joystick signals are only requests. The controller releases the parking brake and commands pump displacement only when all conditions are satisfied. A no-drive complaint after cab work may therefore be an unplugged seat or restraint switch, not a failed hydrostatic pump. Unequal tire diameter, track tension, chain drag, or motor leakage can cause steering drift even with correct commands. Most hydraulic excavators do not have a conventional vehicle transmission. The diesel engine drives the main hydraulic pumps. Moving a travel lever sends a pilot signal or electrical request to the main control valve. The selected travel spool opens, sending high-pressure oil to one port of the travel motor. Return oil leaves the opposite port. Reversing the spool reverses motor direction. The travel motor commonly includes a spring-applied, hydraulically released parking brake. Pilot or loop pressure releases the brake before rotation. A two-speed piston changes motor displacement. High displacement gives lower speed and greater torque. Low displacement gives higher speed and less torque. Automatic travel speed logic may shift back to high torque when pressure rises. The motor drives a multi-stage planetary final drive and sprocket. A weak side can come from pump flow, swivel leakage, valve leakage, brake drag, motor wear, or final drive damage. Motor graders commonly use a direct drive countershaft powershift with several forward and reverse ratios. Hydraulic clutches select direction and speed, while electronic controls manage smooth shifts and protect against overspeed. An inching pedal may modulate a clutch so the operator can position the blade precisely. Backhoe loaders may use a power shuttle with manually selected ranges, a full power shift, or an automatic transmission. A shuttle lever selects forward, neutral, or reverse. A clutch disconnect button can release drive while the operator changes range or uses high engine speed for the loader hydraulics. Stabilizer work usually requires neutral and parking brake. Because these machines combine vehicle drive with demanding hydraulic work, brake, neutralizer, throttle, and implement signals often interact. Diagnose the actual operator control logic shown in the machine's operation and service manuals. Articulated haulers commonly use automatic planetary or countershaft powershift transmissions with a torque converter, lockup clutch, drop box, propeller shafts, differentials, and hub reductions. Retarders may act through the transmission or driveline. The controller coordinates gear, lockup, engine torque, and retarding to control a heavy load on grades. Many rigid mining trucks use electric drive. A diesel generator supplies motors, and dynamic retarding turns the motors into generators. Other rigid trucks use large planetary powershift transmissions. Shift inhibit, body up speed limits, neutral coast protection, and brake interlocks are critical. A truck that will not select a higher gear may be protecting itself because of body position, brake pressure, retarder command, temperature, or a speed sensor, not necessarily because the gear train is damaged. Never bypass an interlock to continue production. Determine why it is active. The transmission controller makes decisions from many inputs. Operator inputs include direction, requested gear, throttle, brake, inching pedal, mode switches, and kickdown. Machine state inputs include engine speed, transmission input speed, intermediate shaft speed, output speed, oil temperature, pressure switches or pressure sensors, parking brake status, body position, seat or restraint switches, and sometimes slope or acceleration data. Other controllers share information over a data link such as SAE J1939. The transmission controller compares commanded gear with measured speed ratios. It can detect excessive clutch slip, an implausible sensor, or a shift that took too long. When diagnosing, inspect the live value of every relevant input while moving the control. A lever can feel mechanically correct while its electrical value remains in neutral. A temperature sensor can falsely command cold oil shift logic. Controller outputs are the actions that make the transmission respond. On a power shift, outputs include direction clutch and speed clutch modulating solenoids, lockup solenoid, lubrication or bypass valves, retarder valves, and parking brake release solenoids. On a hydrostatic machine, outputs include left and right pump displacement, motor displacement, brake release, and flushing or mode control solenoids. On an electric drive, the controller commands inverter torque and coordinates contactors and cooling systems. It can also request engine torque reduction, desired engine speed, or fan speed over the data link. Warning lamps and display messages are outputs too. Use a schematic to identify whether the controller supplies voltage, provides a ground, or sends a pulse width modulated current. Never apply battery voltage directly to an unknown proportional solenoid. Incorrect current can damage it or cause sudden machine movement. Speed sensors allow the controller and technician to see what is actually rotating. An input speed sensor measures the shaft entering the transmission. Intermediate sensors identify the speed of a particular clutch drum or planetary member. The output speed sensor represents vehicle travel before the final drives. In a fixed gear, the relationship between these speeds should match a known ratio. If input speed rises while output speed does not, the active clutch may be slipping or the power path may be broken. If the sensor signal drops out, the controller may interpret slip, inhibit a shift, or select a backup gear. Magnetic sensors need correct air gap and a clean target wheel. Active sensors need supply, ground, and signal integrity. Compare live speed values during a controlled test and confirm that stationary sensors read 0 before replacing mechanical parts. Clutch fill volume changes as plates wear, seals age, oil viscosity changes, or a valve is replaced. Calibration teaches the controller how much current and time each clutch needs to reach the start of torque transfer. During the procedure, the machine must meet specified oil temperature, engine speed, brake, gear, and location conditions. The controller applies clutches in a controlled sequence and watches speed response. It stores fill or pressure correction values. Adaptive systems may continue making small corrections during normal shifts. Calibration cannot repair worn plates, a leaking seal, low pump pressure, contaminated oil, or a sticking valve. If calibration repeatedly fails, read the failure reason and test that circuit. Do not keep increasing values to hide a mechanical fault. After a repair, confirm software configuration, solenoid location, connector routing, oil level, and successful calibration before returning the machine to work. Every transmission converts some power into heat. Converter slip, clutch modulation, hydrostatic leakage, bearing friction, and gear churning all warm the oil. Pump flow carries oil through the cooler and then to lubrication galleries. Orifices and drilled passages feed bearings and clutch packs. A thermostat or bypass may route oil around a cold or restricted cooler. Temperature rises when the machine is overloaded, operated in the wrong range, held against converter stall, driven with a slipping clutch, or when cooling flow is restricted. External causes include packed radiator cores, low engine fan speed, and hot hydraulic oil sharing the cooling package. Measure inlet and outlet temperatures, verify actual cooler flow or pressure where specified, and inspect filter debris. A temperature code is the beginning of a diagnosis, not permission to install a larger cooler or bypass the warning. Heavy haulers use retarders to control downhill speed. A hydraulic retarder may have a rotor connected to the driveline and a stationary housing. When commanded, a valve fills the retarder with oil. The rotor shears and circulates the oil, creating resisting torque and heat, which the cooler must remove. An electric drive truck uses traction motors as generators during retarding. Power is controlled by the inverters and commonly dissipated through resistor grids. Classify the complaint before testing. No movement in any gear points toward an interlock, parking brake, low common pressure, converter or pump supply, broken input, or a common control fault. One missing direction suggests a direction clutch or command circuit. One missing ratio suggests a speed clutch, gear set, or its valve. Delayed engagement suggests drainback, low charge pressure, air, leakage, or incorrect fill calibration. Engine flare during a shift suggests the oncoming clutch is late or weak. A harsh tie-up suggests overlap or an offgoing clutch that does not release. Overheating suggests slip, excessive stall operation, low cooling flow, wrong oil, brake drag, or internal leakage. Noise that changes with gear can identify a gear train or bearing, while noise that follows engine speed may be upstream. Record exactly when the symptom occurs. Start with the operator. Ask when the fault began, whether it is cold or hot, which gear and direction are affected, what load and slope were present, and what repair happened recently. Verify the complaint safely. Check fluid level using the correct procedure. Inspect color, odor, foaming, water, and debris. Confirm the exact oil specification. Inspect filters and magnetic screens according to service instructions. Check parking brake release, linkage adjustment, wiring connectors, grounds, fuses, battery voltage, and visible leaks. Read active and logged diagnostic codes before clearing anything. Save an electronic snapshot if possible. Watch live selector, pedal, brake, speed, pressure, and temperature values. Confirm machine configuration and software. These checks are inexpensive and often reveal the fault without opening the transmission. Parts swapping destroys evidence and can introduce new faults. Pressure testing must follow the hydraulic schematic. First, confirm transmission charge or pump supply pressure. Then check main regulated pressure at the specified engine speed and oil temperature. Next, connect to the affected clutch tap and compare neutral, fill, modulation, and full apply pressure with the specification. Test a known good clutch for comparison. If main pressure is low in every gear, investigate oil supply, pump wear, suction restriction, relief valve, leakage, or an open dump circuit. If main pressure is correct but one clutch pressure is low, investigate its solenoid, modulating valve, passage, rotating seal, piston seal, or clutch. Correct pressure does not prove the clutch plates can hold. Compare input and output speed for slip. Use rated hoses and gauges. Secure them away from rotating parts, and never stand in the machine's travel path. A converter stall test compares engine speed when the driveline is fully loaded and the machine cannot move. The result depends on engine power, converter condition, selected gear, brakes, and transmission clutch holding ability. Stall speed below specification may indicate low engine power, incorrect engine control, converter stator problems, or excessive parasitic load. Stall speed above specification may indicate transmission clutch slip, low pressure, or a converter that cannot absorb torque. But one number does not identify the failed part. Check converter inlet and outlet pressures, temperatures, engine performance, and clutch pressure. Follow the exact OEM procedure, including oil temperature, gear, brake requirements, and maximum test time. Stall creates heat extremely quickly. Stop immediately if brakes cannot hold, tires move, temperature rises too fast, or abnormal noise occurs. For a hydrostatic complaint, first verify interlocks and that the controller is commanding pump and motor displacement. Check charge pressure in neutral and under travel demand. Low charge pressure can cause noise, poor response, and rotating group damage. Compare high-pressure loop readings in forward and reverse under a controlled load. A low reading may mean low command, pump weakness, an open relief, or motor leakage. A very high reading with no movement may mean a locked brake or mechanical final drive problem. Measure pump and motor case drain flow at the specified oil temperature and operating point. High case drain indicates internal leakage, but hoses, flushing flow, and test routing vary. Compare left and right circuits on dual-path machines. Perform displacement or neutral calibration only after pressures and mechanical linkages are correct. Cleanliness is critical whenever a closed loop is opened. Use the electrical schematic and connector views. Confirm controller power and ground under load. Compare selector and sensor values with the physical machine state. For an on-off solenoid, verify voltage and current using the specified test method. For a proportional solenoid, view commanded current and actual current if available. A standard test lamp cannot show the modulation correctly. Measure coil resistance only when isolated and at a known temperature. Inspect for short to power, short to ground, open circuit, high connector resistance, and pin spread. If the electrical command is correct but pressure does not respond, test the valve and hydraulic supply. If pressure responds when commanded by a service tool but not from the operator control, trace the input and interlocks. Never energize a clutch solenoid with the machine unsecured because the machine can move immediately. Transmission debris can identify the type and stage of failure. Dark friction material may come from clutch plates or brakes. Bright steel particles can indicate gears, bearings, plates, or shafts. Bronze or copper-colored material may come from bushings or thrust washers. Aluminium can come from housings or pistons. A small amount of break-in material can be normal after repair, but quantity, size, and rate of increase matter. Cut the filter using the approved method and spread the media in a clean tray. Take an oil sample before draining or adding fresh oil when possible. Do not diagnose from color alone. Use particle analysis, magnetic response, component materials, pressures and symptoms together. If a major failure circulated debris, clean or replace coolers, lines, valves, and converters as the OEM directs. Otherwise, contamination can destroy the replacement unit. Mechanical manual transmissions are efficient and simple, but interrupt torque and depend on operator skill. Power shuttles give easy direction changes, but converter heat and limited automatic control remain. Countershaft power shifts are efficient. When any earth-moving machine will not drive correctly, ask 5 questions. 1. What did the operator command? 2. Did every interlock permit that command? 3. Did the controller, linkage, solenoid, or pilot valve create the expected actuation? 4. Did the correct hydraulic pressure, displacement, electrical current, or clutch force develop? 5. Did torque continue through the expected power path to the final drives? Answer them in that order. Do not jump from a warning code to a transmission overhaul. Do not jump from low speed to a new pump. Use the application chart, hydraulic schematic, electrical schematic, live data, pressure specifications, and safe mechanical inspection for the exact serial number. The architecture can be manual, power shift, hydrostatic, power split, or electric, but discipline diagnosis remains the same. Understand the command, prove each stage, and let the evidence identify the failed component. Before any live transmission test, lower implements, use wheel chocks or track blocks as specified, fasten the seatbelt, keep people clear, and use a trained operator and spotter. Support raised components with approved stands. Hydraulic injection injuries require immediate medical treatment. Hot oil and rotating shafts can cause severe injury. Electric drive machines require the full high-voltage shutdown, discharge, lockout, and absence of voltage verification procedure. This lesson gives a system map, not model-specific test values. For every repair, use the correct operation and maintenance manual, system operation, testing and adjusting procedure, schematic, and safety information. You now know how the main earth-moving transmission families work, what activates each component, how torque reaches the ground, and how to begin diagnosis without guessing. In the next practical lesson, we can open one selected machine and trace every clutch and pressure in its exact gear chart.